So here we go. We were working on the structure of limonene. We were starting from this linear precursor geranyl pyrophosphate. We had recognized by looking at the isoprene units in limonene that the bond between orange 5 and purple 1 we don't need to make because it's already made in the linear precursor. But we had identified this new bond between 5 and 4 in blue here, purple 5 and orange 4, that is not in the linear precursor, and so our mechanism was going to have to explain. And one of the challenges we saw was that we could redraw geranyl pyrophosphate like this, but that purple carbon 5 is trans to purple carbon 1, or it's an E-alkene, which puts it too far away to be reached by carbon 4. Remember, we want to make the blue bond between orange 4 and purple 5, but right now they are too far away from each other. So even though we can envision the leaving group leaving to give you a resonance stabilized carbocation, that doesn't get carbon 5 close enough to carbon 4. Now I tried to explain last time that some of you look at this and say, hey, I can draw a resonance structure in which the bond between carbon 2 and 4 is a sigma bond. Can't I just rotate around that bond? And some of you have even pointed out that in the text, one of the answers, even though they go about showing you this mechanism in the text, in one of their end of chapter answers, they're like, yeah, just rotate around that bond. Doesn't appear to actually work that way, and nature has a workaround. The reason you can't rotate around the bond between 2 and 4 is that that's not a sigma bond. It's a partial double bond, which you can tell by looking at both of these resonance structures at once. There's partial double bond character between 2 and 4, just as there is between 4 and 5. So, to make rotation around this bond to promote the isomerization of the molecule so that carbon 5 can be close to, purple 5 can be close to orange 4, we have the leaving group hop back on to carbon 2 to give you this intermediate. Now you can rotate around the bond between 2 and 4. When you do that, you get to this conformation, and now you should be able to see that carbon purple 5 is now close enough to orange 4 to facilitate the kind of reaction we want to have happen. So this business of leaving group hops off and then back on in a different place is all about getting purple carbon 5 close enough to orange carbon 4 to facilitate a reaction. At this stage, the leaving group leaves again to give us a carbocation that's resonance stabilized, and the difference is, as I said, purple 5 is close to orange 4, close enough to react. Any questions about that? That looks annoying, it looks painful, it looks pointless. Nature doesn't do pointless things. The reason nature does that is to make the isomerization fast enough. All right, and I will draw the resonance structure, of course, in which the pi bond is actually here between purple 2 and 4, and purple 5 has the positive formal charge. Okay? I'm going to keep, even though it's taking precious time, I'm going to keep highlighting isoprene units because I think it helps. Now this step is pi electrons attack an electrophile. You've seen reactions like this before in 351. Sometimes you used an acid or some other reagent as an electrophile, and the pi electrons from a double bond attacked that electrophile. Here, the electrophile happens to be positively charged carbon 5. We make a new sigma bond. Now, notice that there are 2 atoms in the pi bond that we're using as a nucleophile. Atom 2, orange 2, and orange 4. One of them is going to get the new sigma bond. The other is going to get the positive charge. Which one should it be? Should 2 get the sigma bond, or should 4? 4, and the reason that is so that more substituted carbon 2 can have the positive charge, because more substituted carbocations are more stable. That is an example of something you learned about in 351 under the heading Markovnikov regioselectivity. That's what we mean by when we say that in an addition to an alkene reaction, the positive charge goes to the more substituted carbon. All right? So here is now our intermediate. There is the new bond between purple 5 and orange 4. And now you can see we're almost all the way to limonene. The one thing that we're missing is the positive charge on carbon 2. At this point, getting to limonene should just involve an elimination, an E1 style elimination reaction using some base, probably an amino acid side chain from within the enzyme, to remove the proton, and that will give us the limonene product, which I've already drawn above, but which I will copy and put here. Okay? So, yes?
Could the hydrogen be taken from carbon 4?
Could the hydrogen be taken from carbon 4? Good. So one of the things you're noticing is in this carbocation, I've identified one of the possible beta protons, but I think you're pointing out that there's one here. And if you were going to predict products, you would probably predict this one to be removed because that would give you the more substituted alkene. And more substituted alkenes are more stable. Yes, why isn't that proton removed? The answer is, first, is two possible answers. They're equally unsatisfying. So one of them is, this happens in an enzyme active site, and enzyme side chains can, by proximity to the protons, determine which protons they're going to remove. That's kind of hand-wavy. The second explanation is, sometimes there are subtle differences in the stability of intermediates and products that might explain the observed selectivity, but might be difficult to rationalize without some kind of high-level calculation. You're presupposing that this alkene is more stable than this one. It's possible that having 3 of the 6 atoms in this ring being sp2 hybridized might introduce some ring strain. That would be difficult to predict without a calculation, and so that's why I'm telling you it's an unsatisfying answer. So fortunately, you notice that I formatted this question not in a predict what happens, but explain what did happen using reasonable arrows. In other words, you're always going to know where you need to end up. And in that case, you know the double bond's got to be there, so this is the most reasonable step, even if you can think of alternatives. Chances are some of what you're thinking about would lead to other interesting natural products. And I'll show you an example of that in just a little bit. Yeah?
How often does the hydrogen shift to where the double bond goes between 4 and 5?
I don't see a double bond between 4 and 5. I'm missing something.
So I guess on one of the textbook problems, it said, like, propose how the double bond would be between 4 and 5. And it was because there was a hydrogen shift from 4 down to number 2.
From what intermediate?
From...
Oh, I see. Okay. Yes. I'm sorry. I'm back with you. So sometimes you will find that you get different natural products from the same intermediate. And presumably what controls making one versus the other is the enzyme. You're going to hate that answer after a while. But what you're talking about is your basic, I'll show you how to do that from this same intermediate. So I'll redraw the common intermediate. You will discover that a lot of interesting natural products, especially from the terpenes, have common intermediates. This one that's positively charged on carbon 2 is an example. But one of the things you were noticing is if instead of doing the elimination reaction that leads to limonene, what if you did a 1,2 hydride shift? Let me move the number 2 over here-ish. Do a 1,2 hydride shift where the hydrogen leans over with its electrons, breaks its bond with orange 4, and makes a new bond with orange 2. That would put a carbocation on carbon 4. Okay? Is that sort of what you're talking about? Yeah. And then there are a lot of other things that could happen here. For example, I will show you 2 natural products that come from this pathway, but I don't know what one of them is called. I do know what the other one's called. Maybe somebody can Google it, but that's a 1,2 hydride shift. I told you to beware of carbocation rearrangements. Again, your goal is not to predict if they would happen, but given a result, predict that they must have happened. So how would you have known that this had happened? Well, one of the natural products that you can get from this would have been if a base now removes this proton that's adjacent to the positive charge to give you this natural product. And I'm not sure what that one is called, but is that the one from the problem in the text? Okay, yeah. Alternatively, you're going to like this even less. This intermediate here can do something else. So there are multiple branch points in terpene synthesis. Why am I copying and pasting? I don't even know. I think I wanted more space before the drop off. So there we go. Let me redraw this intermediate that we get after the 1,2 hydride shift. Again, maybe it's worthwhile to highlight the isoprene units. Now, one interesting thing that can happen is the pi bond between purple 2 and 4 can attack the positive charge that's on carbon 4 as an electrophile. I don't totally like that because I don't like obscuring the positive charge, so there we go. All right. Now you tell me again, if a pi bond attacks an electrophile, I'm going to form a new sigma bond between either 2 and the electrophile or 4 and the electrophile. Which one here should get the new sigma bond? 4, so that the positive charge can be on the more substituted carbon, right? Sorry? Even if you make a 3-membered ring. You might propose an alternative, but the natural product that I'm about to show you is a real one. Sometimes when drawing these kinds of the products of these reactions, it's useful to keep the molecule in the exact same orientation in your drawing and then draw the new bond even if it looks stupid. And then you can redraw the molecule later to make it look pretty. In this case, I'm going to make a new bond between purple 4 and orange 4 in blue, and it looks stupid, right? That doesn't look like a nice triangle. And I'm going to put a positive charge here. I can redraw that molecule a little bit later if I want by noticing what I've done here. The blue bond has now made, out of one ring, multiple rings. There's a 3-membered ring here and a 1, 2, 3, 4, 5-membered ring there. So what I need to do to redraw this is I'm going to draw a pentagon and a triangle sharing the same edge. Okay. Does that make sense? Here are the isoprene units. Here is the new bond that we made in blue. Here's purple carbon 2, purple carbon 4, orange carbon 4, orange carbon 5. And then you could do an elimination reaction to get the natural product. Again, I'm not predicting this. I happen to know that this is a defined natural product. This one has appeared on exams before. It's not on your current exam. But this product is called thugene. And it's a component of like rosemary oil. I like it because it looks like a duck. But you can see how problematic it is to try to take the standpoint with terpenes. Oh, I want to predict everything that's going to happen. There's too much that can happen. Instead, these lend themselves mostly to mechanism questions where you have to explain what happened. Let me show you. Go ahead.
Is it at the common intermediate that you always introduce like OHs, nitrogens, and stuff?
So when do heteroatoms get involved? Yeah, because one of the molecules we looked at before, menthol, had an OH group. Usually OH groups get introduced when you have carbocations. Yep. Okay, so just a hint on some future, not for this exam, but future mechanism questions. One of the things I'm sure somebody out there is worried about is you've seen mechanism questions before where the question was, which one of these is not reasonable? And here I am showing you a common intermediate that could do more than one reasonable thing. So now you're wondering, what on earth do I do if I have two things, same intermediate, two different reactions, and the question is, are they reasonable or not, and am I worried about that? Here's how I'll format the question instead. I will show you a starting material. I will show you a product like the duck, thugene. And then I will say which of these mechanistic steps does not lead to that product. So, for example, take a look at this one. That is a totally reasonable mechanistic step. That does not lead to thugene. So that would be the answer for that particular format of a question. You got it? Okay. All right. Other questions you want to ask? Let's see, I told you I deal with the question about what about alternative beta protons. So we'll set this up again from this common intermediate. Do you love this common intermediate yet? This intermediate is so common it has a name that you don't need to know. It's called, but if you ever do any reading about terpene chemistry, this is called the alpha terpinyl cation. So now I'm going to show you something else that the alpha terpinyl cation can do. It's going to look a little bit similar to how we made thugene. So the pi bond between carbons 2, and this is going to answer one of your study guide questions. The pi bond between 2 and 4 is going to attack the positive charge, between purple 2 and 4, is going to attack the positive charge on yellow 2. Now, it doesn't look here like that should be possible. It looks like it's kind of far away. But as we count the atoms, you'll see that it's actually pretty reasonable. So first, to see this with a little bit more clarity, I haven't specified stereochemistry before. Let's assume that the bond between 2 and 4 is a dash. That is, it's going down into the plane of the page. And let's imagine that the ring is flexible enough that sometimes this sort of dimethyl tail swings out and gets to be close to almost here underneath the ring. When that happens, this pi bond can reach under, I'm going to show that like this, and attack carbon 2. Again, it will be useful to you. So that's just pi bond attacks or carbocation. it will be useful to you when doing this to sort of draw the molecule before with everything in the same place and then rearrange it later to something that looks prettier. So we made a new bond. As before, we have a choice. Does the new sigma bond go between carbon 2, orange 2s, or between purple 4 and purple 2? The answer is it should involve, the new sigma bond should involve purple 4 so that, I don't know what's going on with the color here, so that the positive charge can be on the more substituted carbon where it's more stable. So purple 2 gets the positive charge, and purple 4 gets the new sigma bond. Whoa, I don't know what happened there. Yikes. And the new sigma bond is going to be between purple 4 and orange 2. So I'm going to draw it here. Like I said, not pretty, but it conveys the right connectivity. All right. Now I'm going to redraw this. I'm going to actually keep the 4-membered ring like this. And I'm going to redraw it such that that carbon 2 that is down is sort of here underneath the ring. So now that's carbon orange 2. This is orange 4. And then here is the new bond that we just made with purple 4. And there's your positive charge. And we can continue to highlight the isoprene units so you can see them. All right, any questions about that? So go ahead.
So why did you go to the form like 2 carbon 2? So it would form like 5, like 2 5.
Why not go to carbon 2 to form 2 5-membered rings that would perhaps be less strained? I think we could illustrate this alternative. And I think you're asking, why don't we go immediately to something like that? The answer is you've got a ring strain issue here, but you also have a more stable carbocation here. And down here you have a less stable carbocation, but less perhaps ring strain. There's a trade-off, and you could also do a rearrangement to get from here to here. I will just say that because this is the product that is observed, it's thought that this one forms first. Yeah. I saw another hand, yeah.
So if you were to draw your isoprene units in the different, like 4 to 5, like if you were to originally draw differently, would you get a different molecule?
If you had originally chosen to draw your isoprene units differently, your mechanism would be different in some respects, but you could still get there. Yeah. In some cases, if you had drawn it differently, it maybe would lead to a different stereoisomer. We haven't worried about stereochemistry though, so that's not such a big deal. Okay. All right, so this intermediate that we've just made, you have 2 different protons that are sort of candidates for subsequent elimination. If we eliminate this one, we're going to get something that's called beta pinene. I'm not going to draw that mechanism. I'll simply draw the natural product. And if you remove this one, you get what's called alpha pinene. And it's possible that I've drawn the wrong enantiomer. We won't worry about that. And so the question of which one gets eliminated, perhaps nature actually generates a mixture of the two. Again, the question for you will not be predicting what happens, but explaining how what happened happened. Okay, any questions about that? Okay, I have in my notes a mechanism for making cedarol, that horrible 5+5+6 membered ring structure that we made previously. I think we're just not going to do that because I'd rather have the time to tell you the story of cholesterol synthesis, which is worse actually than cedarol. So, okay. So here is a 3 isoprene unit linear precursor called farnesyl pyrophosphate. You don't need to know that name. I will highlight the isoprene units. You can see, though I'm not numbering the carbons here, you can see the 5-to-1 head to tail connections in between the isoprene units. In an interesting step whose mechanism has been pretty well worked out by chemists, but which we won't talk about, nature takes 2 of these isoprene units and it needs a reducing agent. In that case, the reducing agent is NADPH, which is kind of like NADH. It's almost identical to NADH, except it has another phosphate group. That's what the P is for. Uses of NADPH are slightly different in biochemistry than NADH. I will defer on that till your biochemistry class. This is a reduction reaction because a hydride and a proton are going to be delivered. The enzyme that does this, you don't need to know this either. I'm just putting it here so you can go back and learn about it later if you want to, is called squalene synthase. And this enzyme catalyzes an unusual reaction that links together 2 farnesyl pyrophosphate units via a 5-to-5 tail-to-tail connection. Normally, isoprene units are linked together head to tail. The unusual thing about squalene synthase is the isoprene units here are linked together tail to tail. So I'll show you that just with color. We'll illustrate the isoprene units. I've only drawn half of the molecule so far. Then I'll draw the rest of it. 5, 4, 3, 2, 1. I did it wrong somehow. Yep, sorry. Here is the new bond, and then 5, 4, 3, 2, 1. So you can see that green carbon 5 on one molecule of farnesyl pyrophosphate gets linked to green carbon 5 on another molecule of farnesyl pyrophosphate. And this molecule is called squalene. And squalene's made in your body. It's a component of like oils in your skin. But this is an important precursor to every steroid hormone and every cholesterol molecule or similar molecule that's formed in nature. It's got 1, 2, 3, 4, 5, 6 isoprene units, so 30 isoprene units, so 30 carbons. A lot of carbons there. It's linear, but we're going to do some reactions on this that are going to create horrible, bewildering complexity. We're going to make 3 6-membered rings and a 5-membered ring all fused together. So I hope you've been following the counsel of President Nelson and eating your vitamins and fastening your seatbelt, because here it goes. All right, so the first reaction, which we're not going to talk about the mechanism, is catalyzed by an enzyme that's called squalene monoxygenase. As you might expect, this enzyme adds an oxygen to squalene. It's going to make an epoxide out of one of the double bonds in squalene, and selectively it's the one on the end. Now you may ask, how does squalene monoxygenase choose the molecule on the end to make an epoxide? And the answer is, I don't know. So here is the squalene epoxide. We're not going to worry about stereochemistry, though it's been well worked out. And this is called, squalene epoxide. Sometimes people call it squalene 2,3 oxide. And then, in an important step, the epoxide gets protonated. Now, here's where we're going to use everything you've learned so far in OChem to walk our way through the horrible mess of what happens next. In your text, what's shown next is done with a bunch of arrows all in the same step. I think we're going to do a lot of copying and pasting and slowing things down so you can see what each individual arrow is for, because each individual arrow, for the most part, follows rules that you already know about. So here's an epoxide. If a nucleophile were going to attack the epoxide that's protonated, which carbon would be attacked? Orange 2 or orange 4? Some of you don't remember. So remember, epoxide regioselectivity for opening of epoxides, it depends on the conditions. If it's a strong nucleophile and the epoxide isn't already protonated, sterics matter most, and you get basically attack on the less substituted carbon. If the epoxide's already protonated, the mechanism is very much SN1-like. The leaving group leaves first, and positive charge builds up on the more substituted carbon where it's more stable. And that's the situation we've got here. So carbon 2, which I'm going to highlight in blue, is going to be the one that does the attacking. Now, have we got any nucleophiles in this molecule? The answer is yes. You got all kinds of pi bonds. Which pi bond is going to do the attacking? Well, let's see if we can find one that's an appropriate distance away. We already said that we expect carbon 2 to be attacked. Right? So let's see if we can find a pi bond that's within 5 or 6 atoms of carbon 2. I'm going to count that in gray now, right? And maybe I'm going to erase the orange numbers to avoid confusion about what's counting where. So we'll start here. 1, 2, 3, 4, 5, 6. You got a nucleophile just in the right place to make a 6-membered ring. Okay? So let's show that pi bond attacking carbon 1 and the epoxide, gray carbon 1, and the epoxide opening up like that. Okay? In so doing, we will have made a 6-membered ring. Right? Now, we're choosing to have carbon 6 get the new sigma bond indicated by the red line here, so that the positive charge can be on carbon 5, and also so that we can make the more stable 6-membered ring. So to predict what happens next, all you got to do is draw a 6-membered ring. You can start the numbers anywhere you want. I'll go ahead and let's just have this be 1, 2, 3, 4, 5, and 6. Sure. Carbon 1 has the 2 methyl groups on it. Carbon 2 should have the OH on it, right? 3, 4, 5 should have the methyl group and be positively charged. And 6 Should have the whole rest of the molecule, right? Will it help if I highlight a little bit? Oh, dang. There we go. 1, 2. Okay. So there we go. You with me so far? That's the first 6-membered ring. Now to figure out what happens next, we need to draw the rest of the molecule. Cannot send message. Oh, Chase still doesn't know that I have his wallet, so hopefully, good luck, Chase. Okay, I will send it to him after class. Apparently my email was not working. He's probably all kinds of stressed, poor guy. All right, so let's just redraw the rest of the molecule, or not. All right, so what we call the R group here is this carbon. So that's the last carbon of the purple isoprene unit. So we're going to have another bond and then the green isoprene unit. I don't really like that. Sorry. Okay. So we're some of the way there. Now, what we're going to do next is ask the same question. We have an electrophile and a pi bond. Do we have an electrophile and a pi bond within an appropriate number of atoms? And again, we do. So this now green isoprene unit is going to, I'm sorry, I'm getting it wrong. There we go. The pi bond in this green isoprene unit is going to attack carbon 1 to make another 6-membered ring. And we can redraw that like this. And again, you're going to expect the new atoms to be linked together, the carbon gray 1 here with the positive charge on it, and carbon 3. All right, so if we redraw that after the step, I'm going to just keep things in exactly the same orientation. We make a new 6-membered ring here. The new bond that we just made is here between 6 and 1. I really don't like that 6-membered ring. Okay, so I can tell by the size of disgust and the whispering that's occurring there that you are wondering whether you really have to know this and whether or not you can just smile and nod and get out of here and not have to worry about it ever again. I have some bad news for you. Okay. So there's 2 6-membered rings that we made. And there's the R group coming off of that. Okay? Each of the steps that we do is going to follow this kind of pattern. Now, the way we're going through it is kind of painful. If you want, I'm trying to show you where each of the new bonds comes from, but in a way, it may be easier to talk through it in the way that your book does. So maybe I will pause and give you that kind of overview. But before we do that, let me continue to highlight the isoprene units. Okay. So the R group here would be, perhaps better would be to draw the carbon there and then put an R group here, and that's the rest of the squalene molecule. Those are the first 3 isoprene units of the squalene molecule. Okay? All right, questions so far? Not too bad if you can count and you focus on pi bonds attacking positive charges and making the bond with the less substituted carbon so that the more substituted carbon can have the positive charge. All right. If your text were doing this, what they would show you would be this. They would show the arrow from this pi bond, the purple pi bond, attacking carbon 1. At this stage, it might be easier to drop back to the way we've numbered the atoms in the isoprene units. Okay, so the first bond, the first attack makes a new bond between purple carbon 4 and orange carbon 2 with a buildup of positive charge on purple carbon 2. The next bond is going to show the formation of a new bond between green carbon 4 and purple carbon 2 with a buildup of positive charge on that carbon. Okay? That sort of describes what we've done, and that's going to create a new bond between green 4 and purple 2. Okay, questions? Yeah.
Will the same thing happen on the other end if you make it enolate again?
Does the same thing happen on the other end if you make another epoxide here?
Oxide, yes.
In principle, it could, though actually before the enzyme only puts one epoxide on, and that's enough to get things going. You're going to see that we're going to have a chain of reactions because, again, we have a buildup of positive charge here, and again, we have a pi bond in just the right place. Okay? So I will show you the rest of that, but my opinion is your level of stress is sufficiently high that the next, I would say, 3 to 4 minutes of your time are wasted if we continue down this pathway. So you still got to know it, but we're going to pull a third Nephi here. Go to your homes, eat, ponder on what you've learned, and get ready because I don't know if you've noticed, in third Nephi, after Jesus sends everybody home the next day, he starts in on Isaiah, so he doesn't give them a break. So we'll see you Friday. Good luck on your exam, and we will finish this on Friday.